In the last webcast, we learned about the nucleophilic aromatic substitution mechanism that involved an addition-elimination pathway. In this webcast, we're going to take a look at another version of nucleophilic aromatic substitution that involves elimination-addition pathway. This pathway involves the creation of a benzyne intermediate, which we haven't seen before. Let's take a look at some examples of this reaction. The first thing to notice in this reaction is that it doesn't have electron withdrawing groups on the ring, as we had seen in the last webcast. Another interesting aspect of this substitution reaction is that the incoming nucleophile does not always end up on the carbon that bears the leaving group. As always, this requires some mechanistic insight to understand the formation of the observed products. As we saw on the last slide, this experiment is treating the three different isomers of bromoanisole with sodium amide, and the mechanism that we will walk through will provide an argument for the observed products. Starting with the isomers of bromoanisole, we can see that they all converge to the same product 5. However, para-bromoanisole has an additional pathway that yields product 13. Let's begin by starting with orthobromoanisole, compound 1, and look at its pathway to compound 5. First, we know that sodium amide is a very strong base and very reactive. The first step is deprotonation of the proton adjacent to the leaving group. This creates the carbanion in structure 2. The carbanion then eliminates bromine. You should recognize these two steps as an E1CB pathway. However, the interesting point about this process is the creation of a new pi bond that creates a triple bond within the ring. This structure is appropriately called a benzyne. As you can imagine, an alkyne with a 6-membered ring is very strained and highly unstable. This is indeed the case, as the benzyne structure has not been isolated. Many experiments have been conducted, however, to provide evidence for its existence. The second step of the mechanism is addition of the nucleophile to the benzyne intermediate. A proton transfer then affords the product. Now let's look at the para-substituted starting material and how it affords two different products. Again, deprotonation and elimination occur to create the benzyne intermediate. The resulting nucleophilic addition step can then occur at either carbon of the alkyne. This yields the amine group in the para position in structure 13 and in the meta position in structure 5. It's important to note that in theory, the triple bond of the benzyne could be attacked at either carbon. However, in practice, this isn't always the case. The most important point is that the formation of the benzyne intermediate does help us explain why the incoming nucleophile does not always add to the carbon that bears the original leaving group. In this lesson, we were reminded that substitution of sp2 carbons do not proceed through an SN2 pathway. However, their nucleophilic aromatic substitution pathways can afford substitution at aromatic carbons. These are elimination-addition pathways that proceed through a benzyne intermediate. Additionally, there's an addition-elimination pathway that is facilitated by electron withdrawing groups at the ortho and para positions of the benzene ring. And finally, we learned that aryl amines can be converted to aryl diazonium ions that allow access to a wide variety of substituted benzenes.